Thank you all for coming. I was asked to introduce our next speaker, which is my great pleasure. Our speaker is Ruediger Urbanke, and when I was asked to introduce him, I was told that I should say something more personal about him than what you can find on his biography page. And so I wrote to several colleagues and friends to get some information. And they told me a few things. One thing they told me is that Rudy is very serious, so no jokes will be told. That was an insistence. The second thing they told me is that the last time that he came to Brazil, he went and visited the Amazon, and they warned me that I should be very careful if I spend any time with Ruediger here, because last time when he was in the Amazon, he likes to bring a few snacks after lunch, and so he had some fruit, some bananas in his pocket as he left. And apparently they were chased by monkeys out of the All right, so that's all my personal information. Some more serious background, there'll be a rebuttal, I'm sure. Oh, there's more personal information. We can all take a turn.
He doesn't want me to say that.
So Professor Urbanke has received his undergraduate degree from Vienna, and then did his master's and PhD at Washington University in St. Louis. He's been at Bell Labs and now at EPFL for many years. He's won many, many awards. Some of them you've already heard about when he sat on the panel yesterday, including 2 information theory paper awards. But what I found most impressive, and I thought you would find very interesting, was if you go to his biography page, you'll see a list of the prizes, all the prizes won by his students, which I think is very nice. I think that says a lot about him. So I will pass the floor to Ruediger.
Thank you very much, Michelle, for this very kind introduction. Kind because you left out many things you could have said. So let me first, before I get started, give you some career advice. Panels are dangerous, okay? If you ever asked to be on a panel, decline, okay? Chandra managed to insult 1 billion people in 1 sentence. And I wasn't quite as successful, but I seem to have offended all algebraic coding theorists, okay? I didn't intend, so I apologize. So bow to all algebraic coding theorists. I'm very sorry if I said anything, okay? Now, let me then thank the organizers, of course, Marcelo, Max, Weli, and all the other people that made this happen. It's really a fantastic place. It's a pleasure to be back. They're taking care of us in such a nice way. This really doesn't feel like work. This feels like Club Med, where you check the box, educational activities. Okay, so it's a beautiful place, and I guess yesterday we complained about the funding agencies, but it's not really that bad, right? I mean, I think we are doing quite well. So let me just see if I forgot to thank anyone. I think that's pretty much it. So what I want to do is I'll tell you a little bit about spatial coupling. Okay. Now this will be divided into 2 parts. The first part, it will be really mostly very, very basic stuff. I want everyone to be on the same picture, hardly any formulas, moving movies and pictures and so on. The second part will be a little bit more technical, but not really much super technical either. Okay, so let's get started with it. So this is of course a diamond, okay, and the diamond is something of value, okay, so that's great, okay, and so if you learned science from movies like me, okay, then you know that diamonds are forever, and then you might get very disappointed, okay, if you find out that that's actually not true, okay? Diamond is only one form of carbon, and it's actually a metastable form, at least metastable in the pressures that, if you bring it up this, I guess if it's on very high pressure, it's actually the stable form, but if you bring it up here, it's actually a metastable form. Now, don't be too worried, the times that it takes to actually get into its stable form is pretty long, so you don't have to be too worried about it, but it's, Okay, I'm sorry, yeah. So you don't have to be too worried about it, but it's not really the most stable form of carbon that is known, okay? So what will happen eventually is that you'll have that, and so, some other advice, okay? You should really go for this, okay? Because if you want to do eternal love, okay, a metastable thing is not what you want to convey, okay? So anyway, good. Now, in this case, metastability doesn't seem to be a very useful thing to have. But indeed, there are many processes where metastability, plays a role, and the physical process that underlies what I'll tell you plays a role. And something that perhaps here, is maybe not as commonly known, like heat packs. Okay, why would you need heat packs in Brazil? But if you go skiing in the Alps, okay, where I come from, then heat packs are very, very convenient. And so there are various versions of this. One thing is filled with this, what's called sodium acetate. And it's a liquid, and again, it has this chemical has two forms: a metastable form, which is this liquid here, and then a stable form, which is a kind of a crystalline form. And so, in this metastable form, you take it with you, and then when you actually want to get some warmth, there's some discs. These are typically metal discs here, and you click on this metal disc, and that starts what's called a nucleation process. So, it starts a process where the crystals slowly grow. And since the crystal form is a lower energy state, what will happen is that simply energy is given off from the higher energy state to lower energy state, and that's exactly what you feel, of course, as warmth. And the nice thing is that when you then take this after the process has been done, maybe it takes an hour or something, you can take this heat pack, put it back into like some warm water, get again energy into the system, and it will go back to this, and you can recycle it. Okay, so in this case, that's very useful, and that's what I learned later on then from physicists. It's particularly Laurent Cascala, Marc Mizar, Lenka Stevobora, and my local physicist is Nicolas Marquis, from which I've learned a lot of these things that relate to these processes. Okay, so metastability can actually be something that's quite useful. And so now the point is that what I want to show you is very much related. So these spatially coupled codes and why they work and how they work, this is exactly this nucleation process that you have seen here, except that we use it to do something useful for processing. And right now I show you everything in the context of coding, but you could do things that has been done in other areas. For example, if you look at compressive sensing, people have used that to come up with special sensing matrices, which then allow you to break through what's called the L1 construction barrier, so you can actually get to the capacities by using this, and this is result by the people I mentioned, plus Andrea Montanari and the students who have done this really impressive work. And you can do this also for other graphical models, but I'll restrict myself exclusively to coding, and I'll restrict myself even further to the simplest case, namely the binary erasure channel. And so one mantra, I think, that that we really learned in the last perhaps 10, a little bit more years, is that you should not be afraid to look at the simplest possible case. Okay, the erasure channel was, maybe until 15 years ago not considered to be, some amazing channel. Okay, erasure channel, right? But this has changed a lot. I think for two reasons. One is that, for file sharing, etc. If you just look, for example, fountain codes, right, like all the applications there, this is actually an imminent practical channel. So, it's actually very interesting to know by itself. And number two, that if you look at it in the right way, it's much easier to come up with results, to see things, insights, to draw things, etc. But also, if you do it in the right way, essentially everything else carries over. It's just typically more work. Okay, it's just more work. It's a little bit more technical, a little bit more mathematical. But if you understand it in the right view from the binary erasure channel, then you understand essentially what's going on. So I'll more or less exclusively limit myself to this case. So now, the first thing we have to do is, in order to a little bit understand what's going on, is we have to look at the basic case. Okay, so we have to look at the uncoupled case before we can look at this, what's called spatially coupled codes. And so I have to spend a little bit some time to talk about the simplest case, namely standard low-density parity check codes, and how they're typically decoded and processed and analyzed over the binary erasure channel, something that I hope many of you have seen, and so we'll just perhaps just bring it into the notation that I'll be using, and maybe familiarize yourself a little bit with the notation and the pictures, because the same pictures will happen. And so I hope I don't bore you to death, but maybe some people haven't really seen it, and otherwise it wouldn't really make much sense if I continue. Good, so what is my setup? It's the very basic standard setup that I'm considering a linear code represented by its parity check matrix. And so you have here your bits, and in this case these are 20 bits. They each can take the value 0 and 1. and these are the constraints we have, and in this case there are 10 constraints we have. We call them parity checks. And so what will happen is I will in particular consider graphs in which in general every node here is a particular degree. Maybe the degree here typically I will draw will be 3, and every check node will have a particular degree. Let's assume degree 6 here. And so these edges indicate simply what are the bits that are involved in this check. So for example, C1 will check bit x6 because you can see it's connected x6 and x7, etc. Okay. Now the rate, what is the rate? Well, we start with 20 degrees of freedom. These we could fill with bits. Then we have 10 linear constraints. And if all these constraints are linear independent, then we have still 10 dimensions that we have left over 20 bits that we send. So this is a rate and a half code, right? But it could happen that some of these constraints were actually linear dependent. And so this rate that we have is in general bigger or equal than what's called the design rate, and this design rate is just has to do with the, just what exactly said, how many degrees of freedom you have divided by the length of the code. Okay, but you can show that for large graph, it's very unlikely that these matrices that correspond to them that they are not full rank. So essentially, you can think of this as the rate of the code. Okay, so this is what I will be looking at this very simple set, and so now I will not really be looking at one such code here, but I'll always do what's called an ensemble analysis. So there are two things that are involved here. I first fix the parameters. So let's say the degree is here 3 and 6. So this we'll limit ourselves to what's called regular LDPC codes. And then once I have this fixed, I will now let this length grow to infinity, and we'll pick these connections randomly. So I think in the next picture this is shown. There are many ways of doing it. One of the cleaner ways of doing it is use what's called the configuration model. So how does this configuration model go? Well, in the configuration model, this is similar to or it's exactly the same as the configuration model that you know from random graphs, hopefully. Maybe if someone has seen a book by Baldabash. So how does this go? If this node has degree 3, then simply make here 3, let's call them sockets here, okay? For each of them, look at the 3 sockets. If this has degree 6, think of here 6 sockets. Now, of course, what we need that the number of sockets on the left is the same number of sockets on the right. And now what you simply do is you pick a uniform permutation, uniformly chosen at random from all the permutations from these, let's say, 12 sockets here to the 12 sockets here, okay? And once you pick that, this is where the edges that are connected to. And so if you pick then a different one, you simply will get a different sampling. And so sampling from that, what we call ensemble, okay, regular 3-6 ensemble, is exactly what I mean with this. You fix the degrees, you pick the length, and now you simply pick uniform at random one such code. And the whole point of this will be that if you let the length grow fairly large, it's not very hard to show that the behavior of almost all these codes are very close from each other. So the only thing that we really need to do is to look at the ensemble average. Okay, so we'll not talk about these what's called the concentration results any further. We'll just assume that the average behavior is representative for the behavior of this whole ensemble, and that's what we'll try to chase. Good. Now, there is a slightly different way, and I will use this a little bit later to represent codes, and that goes back to Jeremy Thorpe, who was a student of McLeese. And this is called the protograph construction, and so it's just a different picture for the whole thing. So I just want to mention it because sometimes it's slightly easier to draw this. So this thing here is supposed to represent exactly the same thing as you saw beforehand. And so this is what's called a protograph. So you see it's again a 3-6 code. Every variable node here, which is blue, has degree 3. Every check node has degree 6. And so the way you get from this to an actual code is by something what's called a graph cover. So how do you know? This is just kind of the template for the code. Okay, it just tells you what the degrees are. But how do you get to an actual code now? Well, you get by this graph cover. So how do you do it? Well, you would take now many copies, okay? And so for me here, I'll draw m is 5, but in reality, of course, codes have lengths of thousands, 100,000, even millions, perhaps even billions of length, right? So you would, this m, of course, in reality will not be 5, but will be perhaps 1,000. And so what will then happen? Well, you take these copies, so think of them as sheets. Maybe you draw one such copy on a piece of paper, you copy it 1,000 times, and now you have them physically laying on top of each other, okay? Exactly perfectly lined up. And this is what this is supposed to represent. And so now take one, what's called an edge bundle. So take one type of edge that you see here, Okay, so you have this 1,000 on top of the other, and you take one type of edge that you see, and you see the same type of edge everywhere on these 1,000 copies, right? And so what you do now is that you now start connecting the different copies that you have by taking a permutation from this edge bundle. So this means simply what you do is you take now this edge bundle, you take these like edges, and now you do a permutation. So for example, instead of connecting this here, you're connecting it to this one here on this layer, okay? And you take the other one here and you connect it here, okay? So now imagine that for 1,000, and so again, the way you would do it, you pick a permutation uniformly and random from these 1,000 elements, right? And then do the connection in this way. And now you don't just do this for this one particular edge bundle, but you do it now for the second edge bundle and for the third edge bundle, and there will be, in this case, 6 such edge bundles. So there will be 6 permutations, each of, let's say, in this case, length 5, but maybe more general length 1,000, and that's how you connect it, okay? So that's another way of doing it. Why might this be nice? Well, there are 2 ways it's nice. It's kind of a very simple language to talk about. So once we have this simple code, it tells you everything, the protograph that you really want to know. If anyway, you're not exactly interested where the connections go, okay? And so if you have more complicated things like the spatially coupled one, it's kind of convenient to draw it because you just need to draw something much smaller. It might even have practical advantages, and we'll see this also later when we talk about spatially coupled. Why? Because if you do that, there's some regularity in there. We'll see this particularly in the spatially coupled one, and this regularity you might be able to use when we're talking about doing the actual decoding in hardware. Okay, so when you can shift in, there's some regularity in these permutations. Now, these 2 ensembles are not exactly the same. Okay, so if you look at the induced probability distribution, it's not exactly the same, but at least asymptotically for what we're interested in, they behave the same. Okay, thresholds and all this stuff is the same. If you look at the actual finite length performance, there would be slight differences. Okay, they are not identical. They induce some slightly different distribution on the set of all bipartite graphs. But for the purpose that we're looking at, it doesn't really matter. So we'll draw both of these pictures and hope that they will, that they will look okay. Good. So now we have defined the code, okay, the ensemble of codes that we're interested in. We pick one randomly out, and now we transmit over the channel. And also for what I'm going to do right now, we'll pick, as I said, we'll pick the simplest class, just the BC. More generally, you could think, of course, of, let's say, Gaussian. You could also think of channels with memory, but right now we have the simplest class of channels. And so what will happen is that we'll send, what we'll do is we'll pick a code, we'll pick a random code word out from this code, we send it over the channel, and the code word is called X, and what we receive is called Y. Okay, so we have here an actual Y, that's the received information. And so now from this received information, we want to, again, figure out what the code word was. And there are in principle 2 ways we can do it. We can do, if we do optimum decoding, we can do what's called bitmap decoding or block map decoding, right? Block map is trying to find the most likely, actual block, the most likely code word, versus bitmap is going to find for any bit the most likely value that we have. And the one that's slightly more natural for looking for HF decoding is the bitmap decoder. So that's what I wrote down here. So when decoding the bit I, under this map decoder, so had this our estimate, what we should do, we should maximize this posterior probability here, right? Given the observation, what's the probability that the value of xi takes on either 0, 1, or in this notation it's plus minus 1, as it's sometimes more convenient. And so, okay, so if that's our setup, if that's what we want to maximize here in principle, then let's write this down a little bit. So the way we were going to write it down is we're going to use base rules. So instead of P of we're going to do 2 things, right? One is base rule and one is law of total probability. So the first thing is, then rather than looking at P of xi given y, let's sum up here, unfortunately I didn't write out, let's sum up and write here P of x given y, but sum up over all the other bits xj. Okay, so that's just the law of total probability. I just add some variables in there and subtract it out. And then what I do is instead of P of xy, I write it as P of y given x, okay? And so once I use base rule, and so this is what we have. So here is the sum. Unfortunately, you can't see this. This should be a tilde x, so this sums up over everything except the xi. Now, what happens here? So what we'll have here is P of y given x, but the P of y given x, since it's a memoryless channel, is just the product of P of yi given xj, yj given xj, so that's just the product here. And then what we have in addition is just the p of x here, and the p of x is a very simple function, right? So in our model, all the code words have uniform probability. So p of x is either 0, you can think of it as either being 0 or 1. It's 1 if x is in the code word, and it's 0 otherwise. Okay, so the exact scaling doesn't matter. Any constant doesn't really play a role in here. Okay, so this is what the decoding we would have to do. And so for the BC, of course, even if we think about the top one, this would be something very simple. Let me just run by it quickly because we won't really use that. Clearly for the BC, this just corresponds to solving a linear system of equations. Remember, every code word has to fulfill the constraint, everything over GF2, that parity check matrix times the code word is equal to 0. Now, if I receive some of the things, okay, the ones that I receive are the gray ones, the ones I don't receive are the white ones. So if I have now two sets, epsilon, the not received part, and epsilon bar, the received part, then I can separate it out, bring all the parts that I know on the right-hand side, and have simply this system of equation to solve, this vector I know, and now this will simply correspond to solving this system of linear equations, right? So this would be easy. Complexity at worst would be inferred by just solving a linear system of equation, and that might even be acceptable, but even for might also not, because if you're looking at very large problem, it's not a good idea. But we don't want to go down this path because this would be very specific to the binary ratio channel, right? And what we want to do is things that, even if we only talk about the binary ratio channel, should be things that we can do for any channel. Okay, so so let's see, how do we actually do the decoding? Well, I hope you have seen this. We do this with these factor graphs. So we're looking at exactly these graphical models as we introduced before, and except that now, okay, so what is the factor graph? This factor here is exactly represented by these code constraints here. So this is exactly what we had here. So what's called the membership function here is exactly given by this part here of the factor graph. But then in addition, we're having these factors here, and these correspond to the received values. So the yj correspond to the xj, and we'll put this factor in addition here. And now what we'll do is we'll use this standard message passing algorithm to do the decoding. Okay. Now, in general, I will not now go over how message passing works in general. I hope that many of you have seen it, but let me just show you how it works for the BC, because right now that's all we really need. In order, if some of you have not seen it. So what is the specific case of the decoding for the BC? Well, the specific case of decoding BC is very simple, okay? And it's exactly message passing in the same way as you have done in high school, okay? You just send messages back and forth, okay? Hope that you you converge to the right solution, okay? And so that's exactly how you do this. And so let me just quickly go over it, how this works. So let's assume we have a very trivial code here. We have two erasures here. Well, what do? Well, you just really send the messages, and the messages are just the received values in the beginning. And you will send them, we'll do a very simple scheduling. So our scheduling will be what's called parallel flooding scheduling, sending all the message left to right, then do some processing, all the messages right to left, do some processing, and back and forth. And so the only thing that's left to do is to explain you what the processing is. It's the natural one, okay? It's basically solving a linear system of equations in a greedy manner, and always trying to see if any of these code constraints here can give us, let's say, the value of this one given the other ones, okay? So what does this mean? Well, we have the messages here, we send them all to the processing nodes, and now we try to see if we can infer anything about the left-hand side, right? So let's look, for example, on the bottom here, okay? So let's see, we want to know if we can decide, for example, what this value here is, okay? Remember that the sum of all these incoming bits must be 0. Well, if both of them we actually knew what the bits were, right, then we could simply take the XOR and we would know what the value is. But unfortunately, there's a second one that's not known, so we cannot really infer anything, right? So we have the two incoming bits here, 0 and question mark. So unfortunately, the outgoing message is question mark. We cannot determine what this bit is based on the value of these two bits that we currently have, right? So no luck. Whatever the message there is just the question mark. But if we look on top, right, then we can very clearly determine what this bit here is, given the value here by this code constraint, because the XOR of the two must be 0. We know that this is 0, so this must also be 0, right? So we know what the value is. We do this for all of them. We send it back, and voila, okay, in this case now on the left-hand side, since we have a value here, right, we have actually determined now this bit here. Okay, so this bit in principle has been decoded. And now we can simply iterate, right? We just go on. Now we send whatever we know back again to the right-hand side, go back to the left-hand side. And we hope that we can do this, and in this case, for this very trivial example, it would actually work. Okay? Okay, so now the question is, how does this actually perform? And all I will talk about today is what's called the asymptotic analysis. So I'm not going to talk about something that's actually very, very important, and probably one of the most important topics right now, which is the finite length performance of these codes, right? How does such a code perform over length 1,000, let's say, over the Gaussian channel? What I'm talking about now is how would such a code perform if I had infinite length and I could look at the asymptotic limit, okay? But how fast this performance approaches this infinite limit that we talk about now is a different question, and it's a more complicated question, but it's also a very important question to answer. So, okay, so now, of course, who did this analysis first? Of course, we have the master in here, okay, Amin. So, I hope I don't say anything wrong, okay? Amin, can you just go outside for a few minutes? Okay, so now, there are two different ways to analyze this whole system, right? So the first one that, of course, Spielmann and, ich don't get the word, Spielmann, okay, did before, which is by a differential equation approach. But I'll show you a slightly different one that goes back to basically, more in the framework of what Gallagher has done, and I'll call it dense evolution. And so how does this work? So first of all, what's the picture? Okay, so we take a code, and now what we do is we take the same ensemble, so a 3/6 code, but we're taking larger and larger ensembles, okay? Make them long, and you should think of that this goes to infinity. Now, once we have something very large, what we do is we pick randomly a graph from this ensemble, and we have seen how we can construct one, right? We take this thing, we do a permutation, and then we pick randomly one of the code words in this graph, and we've seen how many there are, right? And so we take randomly this code word, we send it over the channel, and the channel will introduce erasures. Then we take this message passing decoder that I just talked to you about, right? And when we do the message passing decoder, we just run this iterative process. And one nice thing that happens with the binary ratio channel that's not happening in general is that this decoder is monotone. Okay, so at any iteration, you will either still discover some new bit, you will figure out the value of a bit. But if it happens that at some iteration, none of the bits have been, no new bit has been discovered, at that point you're stuck. You could do an infinite number of more iterations, that's it, okay? So there's a very well-defined limit, because also the number of bits that you have in the beginning is finite, so you either, at worst, after n iterations, you're done, or you're simply stuck forever, okay? So we do this, and we run this until we are stuck. And then when we're stuck, we check whether or not, how many bits are still not decoded. And what we're gonna plot now is the following. We have the channel parameter here, and then we plot essentially, what fraction is not decoded at that point. Okay, so let's try to do this. So we do this for some bit. Let's assume it's very large. Okay, this is just some arbitrary values. If it's a very large erasure, probably maybe that's already half code. We're probably, we'll stuck, and we won't really make much progress. Okay, so we'll be stuck up here and have a very large residual error probability or erasure probability. Now, one thing that's also clear is that, of course, or maybe not so 100% clear, needs a little bit some thought, but you would hope that if the decoder is any reasonable, that if you're making this erasure probability smaller, then the residual erasure probability should also get better, right? It should have some monotonicity properties, right? Would not be very good if it didn't. Clearly, the optimum decoder should have that, right? Okay, so hopefully it goes down. Nothing surprising here. What is then nice is that at some particular point, and we'll get to the description of this point, this changes radically, right? So first we have seen kind of continuous changes of the erasure probability as a function of the channel parameter, but at some point it jumps from some value to 0, okay? So this indicates, this is a threshold, and that's exactly the threshold that we're after, okay? So what this means is that if we are operating somewhere here, and we're doing this experiment, then, with high probability, okay, if we're doing this experiment here and we pick a random code, we pick a random code word, we have a random noise, we do the decoding here, then at the end, with high probability, we have decoded everything. But if we are to the right of this threshold, then with high probability, we end up somewhere actually here. Okay, so this very cleanly separates what's possible under this decoder and not, and so it's exactly this threshold that we're after. Okay, so now, we could do this experiment, but we can do much better. Okay, we can actually, we'll find out that there's a very, very simple answer to what this threshold is. And so how do we do this? So this is now not the differential equation approach that that Amin and Louis and other ones had done initially, but it's more the Gallagher style. So I'll do this by message passing and dense evolution. So remember, we really have two types of operations that are going on here, right? The one iteration at a variable node and whatever the processing has to do at the check nodes. And so what we'll simply do is we'll chase down, how these probabilities behave when they go through one iteration. Okay, so the model will be very simple. So we start. Let's assume we're looking at the variable nodes here, and there are messages that come from the variable nodes, from the check nodes to the variable nodes, and then we have also a received value here. Okay, so now the question is the following: what is the message that I will send out here? Okay, so what will be the message that I send out here? Well, when will I ever send out here a question mark, right? The only time I will send out a question mark here from the processing rules is the following: if all the incoming messages are a question mark and the received value is a question mark. If any of the received value is actually known, then this bit is known. Okay, the erasure channel never makes mistakes. There can never be contradiction. There can never be uncertainty. Once I tell you that this is a 0 and will always stay 0. Okay, so the only thing that can happen is bad is that nobody knows what this bit actually is. It was not a received, and none of its neighbors at that point know what it is. So the only way that this will be an outgoing message will be a question mark will be if all the incoming is on, and this will be a question mark. Okay, so now let's assume the probability that one of these things is a question mark is y, and that they're all independent, and that the probability that this one is a question mark is an epsilon. Okay, and so now what is then the probability that the outgoing message will be a question mark? Well, the only time it will be a question mark if the received one, which has probably epsilon, is a question mark, and all the other ones, each of them y, and how many are there? Well, if the whole node has degree dl, then there are dl minus 1 other incoming messages. So if I'm trying to figure out what the probability here is, then the degree is dl minus 1. So the y will be transformed to epsilon y to the dl minus 1. Okay? So far so clear? Okay, that's how the processing rule works. Now, what about the check nodes? It's almost exactly the same, just with a slight variation. At a check node, remember, it's an XOR. Okay, so the only time I can define one bit is if all the other bits are known, right? Because the XOR of all of them is 0, so I have one equation, and if I want to define what one bit is, then I can only do it if all the other bits are known. If any of the other bits is still erased, I cannot. Okay, so what is now the probability that this outgoing one is an erasure? Well, this will be known if all of them are known. Okay, so the probability that it's known, if the probability erasure is x, the probability that it's known is 1 minus x. The probability that this is known is 1 minus x again to the dr minus 1. Okay, and now the probability that it's an erasure is 1 minus this. Clear? So we go from erasure to probability that it's known. The probability that this is known is just the product, it's just the power here. And now if we want to again go to erasure, probably we do 1 minus. Okay, so that's the processing rule. So probability of erasure x goes to this function here. Probability of erasure y goes to this function here. That's the processing rule for these two things. Okay, so far with me? Good. So now, as I said, this is due to this set of people. If you now go back to the whole overall what will happen. So, what will happen is now the following. Let's assume we do a fixed number of iterations. We do, let's say, 10 iterations, and we want to know what's happening, right? So now, let's look at what's called the computation tree. So I have a particular node, and from this node at the end, I want to know if it can be decoded or not, right? So this node gets its messages from its neighbor, right? So this is the node I'm interested in. It gets its message from its neighbors. Each of these nodes gets again messages from its neighbors, etc. Right? So what we'll get is a whole tree that goes down here, right? Now remember, what we're doing is we're looking at a limit, and I'll comment on this a little bit later. We're looking at a limit. So let's assume we're looking at a fixed number of iterations, and now we're letting the block length go to infinity. Okay, so in this limit, it's fairly easy to show that this computation graph here, okay, this dependency of where the messages come, is actually with high probability a tree. Okay, so all these messages all the nodes that I have in here, they will not be repeating. Okay, so this node will not be this node. Okay, all the nodes you see here are new nodes, different nodes, and through since the channel itself was memoryless, all these messages I have, whether it was an erasure or not, these are all independent events. Okay, so if we're looking at this model here, then it's fairly easy to chase down now what happened. So let's assume I look at this computation tree now of whatever height 5 or whatever this is. At the bottom, I have a probability epsilon of being erased. Remember, the original messages were erased with probably epsilon. And now I'm just checking what's the probability that the message up here will still be erased. Okay, so I go up here. Okay, so we had already the function. This was the check node function. Okay, so this is how this epsilon evolves. It evolves as this. Then I go one step higher. It evolves as this. Okay, remember it was just epsilon times the power. I go again higher. Okay, and I go up. And as the iterations go, I simply have a recursion, right? So YL behaves like 1 minus x to the L, and so on. And so if I put this all together, I simply will see how it evolves. Okay, so after the L iteration, I can figure out what is the probability that bit is still erased. Okay, so we have right now L iterations, we have block length going to infinity. Okay, so now let's think of this. So first of all, for the erasure channel, things are very nice. Okay, so let me first make this a little bit easier. So let me put together what happens in one iteration in one function. So if I'm starting at epsilon and I have an input probability, I have an erasure probability of x going from the variable nodes to the check nodes, then after one iteration, this x will have evolved as this. This is just the composition of the two functions that I talked about before. Okay. Now, when we're looking at this function has a very nice, or some very nice properties. What are some of the nice properties? This function is an increasing function in both its arguments. Okay, that's trivial to see here. This thing is non-negative, and so it's trivially increasing in epsilon, but it's also not very hard to see that it's increasing in x. Okay, so it's a very nice and well-behaved function. And so because it's an increasing function in this, so what we see is that, of course, the sequence, the XL here, must be a monotone sequence. Okay, so we start with epsilon, and after one iteration, it cannot get worse. Okay, you can do better, and it's a monotone sequence. Starts with epsilon, and will never get negative either. Okay, you cannot have a negative erasure probability. So this means the sequence XL that we're looking at here, right, must converge to some limit. Clear? Okay, so we have a non-negative sequence, or a sequence in a bounded domain 0, 1, which is monotonically decreasing. It must have a limit. Okay, and we'll be exactly after this limit. Okay, so this sequence actually converges, and so we're exactly interested in this limit. Okay, so let's look how this behaves. So let's assume we did an experiment. We have here the epsilon below. We're having here the x that I mentioned before, and so let's just plot this. Yes?
Assume that the graph that you showed us, we have a very, very large number of nodes, but it is fixed. So I think there is going to be a limit on the number of iterations that we can do.
Absolutely. So how many iterations can you do in a graph to have independence? About log of n. Okay, so that's the maximum you could hope. If you do more than that, then for sure you will have dependency in there, right? If you're looking at dependency. Okay.
So how can we make sure that we are going to converge?
Let me get back to this question in a second. Okay. Good. So now, so we're having here the epsilon on the bottom. Okay, and so we're just looking right now at the recursion, and we're just looking how the recursion behaves, and we are right now not worried about what exactly that means for the actual graph. Okay. So initially, we start with x, and x is equal to epsilon. So this is why we see a 45-degree line here, right? And so now if we do one iteration, and for each of these points apply this function f of x and epsilon, right? Then we'll see that after one iteration, we'll get a little bit better. And so now remember, for each point here, if I take a cut here, this will simply be a monotone decreasing sequence, right? And so I go further and further and further. I do more iterations, and I know that for every point here, for every cut here, this sequence must converge, right? And so what I'm interested in is what is this limit? And so what you can clearly see here is, right, that if I'm above a certain threshold, this limit will be some non-negative, some strictly positive value here. But if I'm below this threshold, this limit is actually going to be 0, right? And so it's exactly this limit that we're after and that we're trying to characterize. Okay, so now of course limit being 0 should mean for us that the decoding will be successful, right? So that's the significance. Okay, so where is this? Well, roughly if you do this experiment, it's about 43%. And so now there's something that in the beginning picture I slightly cheated when I told you what I plotted. So what we actually, there are two things that we could plot, or there are many things that we could plot. One is the actually erasure probability that I have in the system at any point in time. That's the x, okay? So I'm plotting the x. And so we could have done this. The other one is a slightly different function. Okay, so what is the x? Remember, the x as an incoming function of the y is simply the epsilon times the y times the degree minus 1. Okay, that's how the x was defined. Now, it will be slightly better, and we'll get back to it why, to plot something slightly different. Let me call it the exit function, and that goes back to Stefan ten Brink. And this will be a slightly different function. So this is only what I'm going to plot. I'm not changing the recursion. All I'm doing is at the very end, when I plot things, I'm not going to plot the x versus the epsilon. I'm going to plot this, the exit versus the epsilon. And so what is the exit? The exit is slightly different. So you can see there's no epsilon in here. On the other hand, you have y to the dl. Okay? So what is the significance for this? The significance is the following. Let's assume you've done now as many iterations as you want, and you get stuck. Okay? So what is the best local estimate that you can make about the bit? The best local estimate that you can make about the bit would be, its probability would be y to the dl, because you can use now all the incoming messages. At the end, you want to make the actual decision, okay? But we don't have the epsilon in here, right? So the really best local estimate would be epsilon times y to the dl, okay? So for some reason, and we'll see why, we don't want to put the epsilon in there. But that's only a trivial change, right? We know that the epsilon is there. I can always just, it's just, I'm plotting something slightly different, okay? But it doesn't matter. And also it's clear that these two are trivially related to each other, right? The epsilon is known, so this is no difference. And of course, I can always go from this to this by just taking the appropriate power, okay? So there's not really any difference. It's just a slightly different function, but we'll see that this is the right function to plot. Very nice things will happen if that's what we're plotting. Okay, now, of course, the picture would look exactly the same, okay? If we're now plotting the exit value, the difference is that instead of, remember, originally we had the function y was 1, but the epsilon was there, so we had a 45-degree line. But now, since we no longer multiply by epsilon, initially it will be a constant here. But other than that, it will look the same, okay? If we now apply the function and always plot the epsilon, it's the same, it's exactly the same thing, it's just a slightly different parameterization of the curve. Okay, so that's what the curve looks like, but of course the threshold is exactly the same. So now I can go back to my experiment and just see how the experiment matches up with this computation here, right? And so indeed in the experiment that I showed you before, and I had already plotted the exit function and not the actually error probability. And so I remember I do this experiment. And so now I know actually what this thing should be, this point should be, and indeed I can plot now this curve. And if you look at very large block lengths, you will see that there's actually a perfect agreement between these experiments and this computation. So now let's just go back a little bit to your question. Okay, so you had asked about the question. For the binary ratio channel, this question is actually very easy to answer. So your question was the following. Right now, I kind of a little bit cheated, of course, right? So I looked at one particular limit, and it's not so clear that this has engineering, action engineering, purpose, right? What did I do? I said, well, I think of very, very large block lengths, right? But I only do basically a finite number of iterations, and only once I've gone to infinite block length, I let my number of iterations increase, right? I mean, that's a perfectly valid limit. There's no problem. The only question is, let's assume you do the other one, right? So let's assume you did the limit in which you have a fixed block length, and now let the number of iterations go to infinity, right? That's more what you do in practice, right? And so it's not a priori clear that these two limits are the same, right? And of course, if our computation, the limits were not the same, right? Then this means the system might not be very stable to the exact thing that you're doing, and then it's not so clear what this actually would mean. Okay. Now it turns out that for the BC, we're lucky that one can show that actually these two limits, you can take them in any order, you can take them jointly, it doesn't matter, okay? And the reason for this is that there are essentially two kinds of analysis. One is exactly the one I showed you now, and the other one that goes back to a mean with the differential equation. The one with the differential equation corresponds essentially to exactly the other limit, okay? Versus the one I show you here corresponds to the limit that I've shown you here now, okay? And because of the monotonicity of that's involved for the BEC, you can show that since these two limits are exactly the same, that also any other limit that you take jointly, you take maybe whatever the number of iterations being a function of the block length or whatever you do, the limit is always the same, okay? Clear? So that's for at least for the BC, there's a very easy answer to this. Yes.
The number of
No. So I'm looking at two limits now. One in where first let the block length go to infinity, then the number of iterations, versus first the number of iterations go to infinity, then the block length. These are the two are the same. Okay? So when I first let the block length go to infinity, then the number of iterations, then this analysis that we did is valid. Okay? Because this tree will be a tree with probability 1. Okay? Versus the other one, okay? It's not so clear what happens after a certain number of iterations. Okay? And so, it needs a different kind of analysis. Okay? Clear? So, so to show this, we would need to look at it both, and so, but this is a faster way to get to the final result. Good. And then I talked about the concentration. Okay, so now let me simplify it even further. Okay, so let's assume we believe now that this is describing it. Let's describe it in a static way. So far we had a dynamic way, right? So the dynamic way had to do with, we have a dynamic process, we start with x and then we go down and we see what the limit is, okay? But we'll see that there's actually a static way of doing it, and that goes as follows. So remember again, we had our recursions, x starts with epsilon, and then we do one iteration, go to the y, then we go again to the x. And if we all put it together, it's this recursion that we deal with, okay? So now, since we know that in the limit, this thing converges, okay? What we can just do, and this function here is a continuous function here, then what we can simply do is look at the fixed points of this fixed point equation here. Okay, so remember, in general, we would have here xl plus 1 is equal as a function of xl, right? But we know that the x's actually converge, and this recursion here, or this function here, is a continuous function in its parameters, okay? So this means that the actual fixed points that we get must be, or the points that it converges to must actually be fixed points of this equation here. So we're simply dropping the parameter xl plus 1 and the parameter xl here, and simply write down here a fixed point equation. Clear? Right, so I have recursion x is f of x, right? Or xl is f of x minus l minus 1, right? I know that this converges, and if the function f is well behaved, then what it converges to must actually be a fixed point of this equation x is f of x. Clear? Okay? Good. So this means I didn't have to actually run this. I could just look at what these fixed points are here, right? Which is easier, right? Okay, so if I do this, indeed, I will get, if I'm plotting now these fixed points here, and I'm plotting them, that's exactly what I get here, right? I mean, that's exactly the same thing as I did before. But now I'm not actually running something and then look at the limit. I'm just solving this equation here, and it's an equation between epsilon and x, right? So I'm just looking for every epsilon here, there's some x's here, right? And I'm looking what this behaves. Clear? Okay, now, there's a slightly even easier way of doing it, okay? And why is that? Well, okay, if I'm starting with an epsilon and I want to know what the x is, so remember the epsilon is here, and this is essentially the x, it's just some function of x that I'm plotting here, then this is kind of a pain, right? Even if these degrees are small, this is a fairly high degree polynomial, and I basically have to find the roots of this polynomial, okay? It can be done, of course, but it's not so trivial. There's a much easier way to do it, right? So rather than trying to find an x as a function of the epsilon here, why don't we find the epsilon as a function of the x? Okay, after all, it's the same equation, right? And I'm just trying to find a relationship between the x and epsilon, but it's much easier to find the inverse function, right? Why is that true? Because the epsilon only appears in a trivial way in here, right? The only way the epsilon appears is linear, right? So I simply take this part here, divide it, and I get x divided by this part, and so I have now epsilon as a function of x. Everyone sees that, right? And now it's also unique, right? So for every x, right, this is just a well-behaved function here. For every x, I get here an epsilon. Clear? Whereas beforehand, for a particular epsilon, there could have been many x's in principle, right? Clear? So let's do this. Right now, it's trivial to do this parametric plot, right? I simply plot here, let's say x, or a function of x, and here simply epsilon of x is here, right? And I do this parametric plot, right? That's trivial. Nothing, no recursions, nothing. So I can do this. And so now what we see is that if I'm now looking at, if I sweep x between 0 and 1, okay, so I go between 0, and I go from 1 to 0, then I'll see that I get actually a curve, and the top part of the curve is exactly this, but I'll see some bottom part of this curve here too, okay? And so let me now tell you a little bit what these are. So there are other fixed points that beforehand I didn't see, right? So the fixed points that I beforehand saw were the ones that when I start up here, it's the first one that's hit, right? So I'm starting here, go down, and I hit this. But I never saw this fixed point here. Okay, these are what's called stable fixed points. These are unstable fixed points. This is fixed points that the algorithm never gets to. Okay, so I didn't see them when I run this dynamics of the algorithm, because even though they're fixed points of this fixed point equation, the solution of this fixed point equation, I never get there if I start dynamically from 1. Clear? Now, it turns out that actually these fixed points are as important as these fixed points when we do the analysis. Okay, we'll see. So it's nice to have this whole picture. So now let's see how this, so these are stable fixed points, these are unstable fixed points. And okay, just let's go back to one thing. So let's just summarize here, right? So all I need to do once I have the degrees, I know this function here, I have epsilon of the x, I plot the whole thing here, and where's the threshold? The threshold is basically if I'm dropping down a line here, a vertical line, and I shift it as far as I can to the right, it's exactly, you know, this the point here that's the furthest to the left. If I go down here, these are exactly the 43%, right? So in this picture, I see clearly the threshold of iterative decoding for the uncoupled code, but we'll see that I'll see much more in this picture here, okay? So everything clear? Okay, so more or less, okay? So what we have is, yes?
You plotted exit here.
Yeah, I plot x. I could have plotted the x here, okay? The curve would just be a little bit more warped, but
It was not in the exit equation.
the epsilon, no, so, okay. There's always the channel parameter epsilon in here, okay? The final thing that I'm plotting here, you could think that I plot x, okay? The curve would just look a little bit different, and it's just a rescaling of the curve, and you will see why I want this curve to be this. And the function of this is simply some function of x, which does not involve epsilon, but there's always the epsilon on the bottom, okay? So it's just that what we're plotting here, does this involve also epsilon or not, okay? And in this case, it's the exit function, which is just the 1 minus x to the dl to the dl, okay? That's it, okay? That's what I'm plotting. But you could have plotted just x, would have just looked slightly different, this curve, okay? Clear? Good. So, now, okay, let's summarize. So we have an uncoupled code. We have, we do message passing decoding. Okay, it works by having, and we're just looking at the erasure channel. We start with an erasure probability epsilon. This epsilon will evolve as the function of the iterations. Okay, and so it will converge to some fixed value, and the value depends on where the epsilon starts. If the epsilon is small enough, this value will be 0. If the epsilon is larger, this value will be a non-zero value. And you know, there will be a separation where this, you know, where there's a threshold here, and we can determine this threshold in this simple manner by just plotting this function. We'll get something that looks like this C-shaped curve that's true for all regular LDBC codes. We're just looking at the leftmost point on this curve. We're dropping down the line, and whatever parameter is, that's the threshold for the iterative decoding. Yes?
About that figure, I know that I think that there are some cases that the slope of drop down is not like that. I mean,
So,
is there any solution
yes,
to use
so
that specific
okay.
one?
So for all regular LDBC codes, it looks like this. The only exception is if the left degree is 2, okay? If the left degree is 2, it looks a little bit different, okay? Now, if you're looking at irregular ones, you can basically get any funny shape you want, okay? It will always be a curve, but it will always be a curve if I'm always a function if I'm looking like this, okay? But it could have any number of twists and turns, etc. Okay? But right now, all we will need is regular ones, and our degrees, if anything, will be going up. So we'll ignore the degree 2, which is anyway not a good code, and so that we don't get confused. Okay, so for us, no matter what, as long as it's an LR code with the left degree being at least 3, it will always have a shape like this. Okay? But you're right that if you have irregular, whatever, you can basically, it's basically an interpolation problem. You can give me any number of points and you can find a curve that interpolates on that. Okay?
The threshold depends on the ensemble being used.
Yes, so this curve is a function of the L and R, right? You see, the only thing that plays a role in here is the L and the R, right? It's a function of L and R. So this curve is an L and R, and the threshold is exactly this, okay? Is this number, right? So you plot this function for different L and R, and so now what is the significance? L and R determine the rate, the rate is 1 minus L over R, okay, so that's the rate. And it also determines the threshold in this manner, okay? And so for the erasure channel, what you would like to have is that this threshold is roughly 1 minus the rate, okay? If you can get that, then you have a capacity achieving the distribution, okay? Good. Good. Okay, so now we want to do the same thing for these coupled codes. And so before we do this, I have to first tell you what these coupled codes are, okay? So how does this work? So there are many ways of how you can represent it, but first take simply, this is again our standard code, okay? And again, I draw this as a very small example, but think of this already as a large code. Maybe it has already length 1,000 or something like that, or 100 or 500 or whatever, okay? I'm just making a very small example here. So now what you do is you take many of those, okay? And so one way to do this is to maybe think of them as being on a circle, okay? Fine. So far, they are not connected, okay? Each of them is a code that behaves, and let's assume each of these code is exactly a code, the same code as before. And so it's exactly one of these 3-6 codes that I talked about. Doesn't matter exactly what the connections are, but statistically speaking, it's the same code, okay? It comes from the same ensemble. So each of them would have a behavior in exactly the same way as it did. Now, of course, the whole thing represents a code. If there are, let's say, L of these codes here, the whole thing is also a code of length L times that much, but it has exactly the same behavior, right? So it wouldn't be a very interesting thing to do. So the interesting part comes in by now trying to connect them. And there are, again, many ways of doing it. So the way we'll connect them is by simply connecting neighboring codes here. So the way I will do it is the following. I'll take, so you saw this edge here. So one way would be the following. Take one of these edges that you have in here, okay, and flip a coin that has, let's say, 3 sides. And if the coin comes up left, then you're going to take this edge and connect it to your left neighbor. If this coin comes up middle, you're going to connect it within the code, the positions you are. If the coin comes up right, you're going to connect it to your right neighbor. Okay, so for example, in this case, right, the edge was originally here, but the coin came up left, so instead of connecting it inside here, I connected it to some guy on the left. Is this clear? If it can come up right, I would have taken this connection and connected to one of these checks over here. Okay? So this is one simple connection pattern, and so you do this now for all of them. The only thing that's important is that you do it in such a way that the degree distribution is actually not changed, okay? So this is not a very good example because they have various degrees, but let's assume that they all had, let's say, degree 3-6 originally. Then after you connect them, and now you can see this is like a picket fence, right? This is just like a chain, okay, chain link, and just things connected. The only thing that's important is that every node in here, let's assume, would still have degree 3. Let's say every variable node would still have degree 3, and let's assume every check node here would have degree 6, okay? So locally, the code knows nothing about this global structure, right? So the local structure is exactly the same as what we talked about before, but there's an extra global structure that we have on top of this. Clear? Okay. So now, if you did that, and you would use that code now how would that code behave? It would behave in exactly the same manner as before, okay? So far we have gained nothing. It would simply be that at every position here, if you think about it, right, there's nothing different. Locally the structure is the same. If we don't do 10 iterations and these lengths here become large, okay, then it's again exactly the same computation tree that we did before, and it's exactly the same computations that I do. It will be exactly the same limit, will be exactly the same curve, will be exactly the same threshold. Okay? So this alone doesn't do anything. Now, what we have to do is we have to break, we have to break the symmetry. We somehow have to get this code started, and there are many ways of doing this. One way to do it is the following. I can take I do the following. I can take, for example, one layer here of variable nodes, okay? And what I could do is that I'm simply taking this layer of variable nodes and I'm setting these values to a known value. For example, I'm setting them all to 0, okay? And so I set this value all to 0, and this is known that the value is 0 at the encoder and at the decoder. Clear? So I fix this, and that's in my code description. My code description is exactly this code here with all the connections, plus that these bits here are actually known to be 0. Okay? That's my code description. Now, we'll get back to it, but of course there's some effect, and that has to do if I'm setting these bits to 0, what is the rate of the code? Well, we said the performance is exactly the same as the previous one. The rate is also exactly the same as the previous one. But now if I'm setting some of the variable nodes to 0, I will of course have some rate loss. Okay? And we'll have to get back to this because this is a very important parameter. Okay, but we'll ignore right now that we have the rate loss. So if I set these bits to 0, then if this bit is known and I'm looking at the message passing, then these messages will simply be always constant to be 0. Okay, the message is going from here to here, and the message going from here to here. And if I have a message that's simply, a known message, a known value 0 going into the check node, it doesn't influence anything. So what I might still do is I can simply just delete this. Okay, I can simply forget about those and delete them from the graph. Okay, it's exactly the same. Okay, simply has to do because these messages have no influence. But now you can see that this is essentially like I had just cut with a knife, and cut these things away. Okay, so now I've broken the symmetry. So now this is no longer circular symmetric, but there's some boundary in here, right? The boundary has two effects. One is I have a rate loss. That's not good, but we'll see that we gain some. Good. So now, because of this, it might be slightly nicer to represent it actually on the line. And typically now from now on, we'll actually represent this code on the line. Okay? So internally, this code looks exactly the same as we did before. And every node here will be degree 3. Let's say every node will be degree check. Will have degree 6. But at the boundary, it will be a little bit different, right? You can see since there are no connections to the left, some of these boundary nodes here, the check nodes that I have here, will have lower degree, right? And low degree is good. If a check has a variable node should have high degree. This means it has many ways to figure out what its value is. But a check should have low degree because a check, if a check has very few degrees, then it's very likely that it can tell its neighbor what the value is based on the other ones, right? If I have a check of degree 100, even if a single guy is not known, it's basically useless, right? But if I have a check of degree, and that can happen very likely, right? If it's degree 100, but if a check is only degree 2, it's not so likely that the neighbors are not known. Okay, so now what are the parameters? Okay, so there's first the parameter that has to do with the connection. Okay, remember that I told you I either connected to the left neighbor or stay or the right neighbor. Now, a more general model might be that I connected to neighbors in the neighborhood of size W. Okay, now for us it's enough to just think of W being just what we did. Okay, just nearest neighbors. But this parameter for the analysis, it does play a role, but for us in practice it really doesn't play a role. Okay, then there's the length of the chain. Okay, so this is the length that we had here, and how should you think of this? So this you should think of 2 or 3. How should you think of this? Maybe it's 20. Okay, maybe I take 20 such codes that I'll do, and we'll see how we should choose these parameters. Okay, it's kind of already clear. Remember, there's this rate loss that I have, but the rate loss gets amortized over L, right? So whatever bit I set here, if this L, the rate loss gets divided by the length L. So I want to choose the length L large, so that the rate loss is small. Okay, if L goes to infinity, the rate loss is 0. Now, why might I not want to choose the rate in L to go to infinity? Because of course the code length, right? The total code length is this L times the second parameter, which is this M, namely how many bits I have per position. Okay, and so the total block length is M times L, and we'll see that there are basically two types when we talk about the rate loss, two types of losses that bound us away from capacity. One is the rate loss that I have here that gets amortized with L, and the other one is the rate loss that I have, or is the loss to capacity or gap to capacity due to a finite M. You might have heard that any code length of fixed length M cannot achieve capacity. It can only get so close, and how close it can get, that's it's called finite length scaling. That behavior for optimum codes is like 1 over square root of the block length. Okay, we'll get closer to this. Simply has, we'll talk more about it later on. This simply has to do with the variations of the channel. So I can, if I want to fix the block length, on the one hand I want to make this large because then I can do this finite length scaling gap very small. On the other hand, I want to pick that large, right, because I want to do the rate loss. And so clearly you can see that there will be some optimization going on. Okay. So you should think of this as hundreds or maybe 1,000. You should think of this maybe 20. And so spatially coupled code will not be your choice, your favorite choice if you have dealing with very small block length. Okay, if we're doing hundreds or maybe 1,000, that's very unlikely to be the best way to go. Standard LDBC codes are still the things to beat there. But if you're able to afford longer ones, think for example of optical, then that might be a very good choice, and we'll see why. Good. Okay, and then we have the actual parameters, so the degrees, let's say 3, 6, or whatever we're dealing with. So this is the ensemble that we deal with. Okay, so now as I said, there are basically several ways of thinking of this ensemble. The one I told you now about is kind of the random one, right? Where you think of that, as we talked about before, and that I simply take every edge here, I have a certain window, and that then I'm basically mapping it to one of these checks in this window. Okay, so this is, let me call it a random construction, where I simply flip a coin and I'm looking of where I'm actually connecting to. And so that's the one we'll actually be using then for the analysis. But there's another one, and it has two advantages. Number one, it gives prettier pictures. Okay, and number two, it behaves better. And actually, there are three reasons. Okay, number three, it's actually could be much nicer for if you implement it in an actual system, because you have more regularity. So it's something that performs better for finite length, has fewer number of iterations, and also has a lot of structure that you can use in implementation, but it's more difficult for the analysis. Okay, it's just because of the structure, you have more parameters around. So how is the other type of code? How does this work? So now what we do is, remember, these are the protographs. Each of them is now representing one of these codes of, let's say, length 1,000. Again, it's a 3/6. All the nodes are degree 3. All the nodes are check nodes degree 6. And so now how I do it? Well, for example, one way is that I'm now, instead of randomly mapping it, maybe every check node has now exactly one connections in here, one connection maybe to the neighbor to the right, and one maybe connection to neighbors to the right. Okay. So before I did it randomly. I said, a check node for every edge I randomly picked. But now maybe I say there should be exactly one of each type. Okay. So it's a more regular structure, and I can do this for all of them. And so now that's my structure of the code. Okay. So now. Let me first go through to see what happens at the boundary and then tell you how to think about this picture, right? It's a pretty picture, but how should you think about it as a code? So if I do this, right, you clearly see that there's a little bit some problem at the boundary because you have some edges that go outside here, right? So you're going some edges that go to checks here, and there's some edges that go to variable nodes here, right? So, this is now the termination. That it's exactly the one that corresponds to cutting this thing that I had. So there are many ways of dealing with it. So there's basically some missing variable nodes that I have here, and there's some check nodes here, right? So how can I do it? One way is like this. I can assume that these variable nodes are here, but they're set, let's say, permanently to 0. Okay, that's exactly what I did beforehand. And here the check nodes I can simply add. Okay, so that behaves. So that's one way to do it. And there are many other ways to do the termination. That's actually one of the, I think, most important, open research topics still, to find the optimum way of doing it. Right now, I don't want to get too much into the detail how to do it. This is one way that works.
So the rate class is proportional to W.
Sorry?
The rate class is proportional to W.
We'll get back to it. Right now, the way I do it, it will be W over L. Okay? But we'll get back to it. It can do much better. Okay? Good. So, so now these variable nodes that are here, but set to 0, again, they have no effect. I can get rid of them. These check nodes are still here, right? And so now you can very clearly see the rate loss here, right? So you see here, in this case, W is 3, so it will be W minus 1 extra check nodes that I have. That's the degree of freedom that I have. And so that will be the rate loss. So W minus 1 over L, in this case, would be the rate loss. And now if you wanted, you can maybe just move this a little bit inside, right? The relationship of this to this, where you draw it, is completely arbitrary. So if you simply move this and symmetrize it, you get a picture like this, for example, right? So how should you now think about it? Okay, so this is the code here, but that's just the protograph, right? That's just the template. So now do it again. Put this on one piece of paper, right? Make 1,000 copies of this, okay? Make 1,000 copies of this particular template, and now you will have again edge bundles. So there will be 1,000 of edges of this type, right? On each of these pages, you have one such, right? You simply do a random permutations with them all, right? And then you have 1,000 of the other ones. And for every edge, you simply permute randomly. Clear? So this is just a template. This is not the actual code that you see.
First do the protograph, and then you do the...
Right, so, exactly, yes. Okay. Yeah, so since you can think of this already also as a lifting, you can basically think of two liftings, okay, but it gets complicated, okay? So whatever is easier for you, think of it either in the previous model with just random things, random codes, random constructions, just randomly, where you just connect neighbors, or think of this protograph, it depends, okay? Whatever is easier. It's for us, for our purpose, it's the same. Okay, so as I said, the protograph construction is the one that you really want to use probably in practice or something like this, and there are many variations of this. I just gave you one. It has better performance. It's very suitable for implementation because there's a lot of structure, but it's a little bit more tricky for analysis because it has more parameters, because these edges now, it's not the same. In a random thing, any edge is basically the same statistically speaking, right? But for this one, depending if the edge goes to the left or to the right or to the right neighbor, it has different statistical properties, and so you have more parameters that you have to chase, okay? So it's simply more parameters that you have to analyze, and that's why you would not, you would not go maybe for the analysis first for the photograph. The random construction is better for proofs, has fewer parameters in there, but it's not as good when you, asymptotically the same, but for finite length it's not as good. Okay, so now, I gave you this construction, okay? Why on earth might you want to do this construction, okay? There's nothing right now. The only thing I have right now is that we have a rate loss, okay? Not a very good start, so hopefully we get something back, okay? And so let me just, first give you some intuition of why it might be good to do the coupling, okay? So this will not give us the actual threshold of the code, but it will tell us a little bit why that actually might be a good thing to do. And so what I want to show you now is that these codes, that when we increasing the degrees, the uncoupled one and the coupled one behave in a fundamentally different way, okay? And in particular, we'll see that the uncoupled one, if the degrees actually augmenting, if they're increasing, then the threshold will go to 0, but for the coupled one, it does not. Okay, so let me just show you. It's actually fairly easy to do. So what we're doing is the following. We're looking again at this curve. Remember, this is now the curve that I showed you before, and this was for the 3/6. And all I'm going to do now is that I'm gonna now increase this degree. So instead of a 3/6, the next one will be a 4/8. Okay? It's exactly the same curve that I drew now for the 4/8. And what can you see, right? So if you look back again at this thing, you can see that the curve moved a little bit to the left, right? So you can see that threshold is now worse, right? This is 0.3, this is 38%. Before it was about 43%, right? Now let's go further, right? So this for the BC, 510. 714, 1020, blah, 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 okay? And so what you can see is that this goes to 0, and that's not something that's very particular for this case, not for the BC, but it's something that is true in general. And you can actually show that the following, that this is basically the threshold here expressed as the entropy. So for the erasure channel, that's just the threshold here, the epsilon star, okay, just this value here, okay? And you can find an upper bound on this threshold. And the bottom part here is basically just goes to 1, so ignore it. So what this upper bound says is that the threshold behaves or cannot be larger than the binary entropy function by 1 divided by essentially the right degree. Okay? So there's a 2 in there and there's a -1 in here, we have the square root. So if the degree goes to infinity, this goes to 0, and the binary entropy function will also go to 0. I'm not claiming that that's a particularly good bound, but it does what we want it to do. It goes to 0 as the degree goes to infinity. Okay? So no matter what the channel is, if you simply take a regular code and you do this experiments, the equivalent of dense evolution, you compute the threshold. The threshold for regular codes, as the degrees go up, will actually go to 0. Okay? So that's not very good behavior. Okay, now let's go now to the coupled codes, okay? And we do exactly the same. What we'll do is we'll also increase the degrees, and we'll see if we can find a trivial bound for the threshold there. So how does this go? Well, this is exactly the structure that I showed you before. And now, in order to do this point, I'll do something slightly different because it will make it easier for me. And what I will do is the following. Every edge here is actually a double edge. So every bold edge, that's why they're black, okay? This very stark, very strong bold face edges here, is that this indicates these are actually 2 edges. I was just too lazy to draw 2 edges here. Okay, so this degree here is actually not this doesn't have degree 2 but has degree 4. And this doesn't have degree 3 but has degree 6. Okay, so it's the same like this. I'm just making all the degrees twice as large. Okay, good. Now, what I will do is the following. I want to decode this now with a binary erasure channel, right? So this is right now a 612 regular coupled ensemble as we had beforehand. And so now what I do is the following is I'll transmit over the binary erasure channel. And so maybe let me just go back with this again. So it was a little bit too fast. So look at this. So we're having the nodes here, we're having the check here, nodes here, and then we're having something extra on the right here. Now for the binary erasure channel, it's fairly easy to see that if you have some extra edges coming into a variable node, they can only help. Okay, they can never hurt. You never get contradictions. You never get errors in. The only thing it could be that someone tells you from the right what actually this value here is, right? So this can only help you. So let's assume I simply ignore it and take everything from the right away, right? So this gives me a code that cannot be any better than the code. So the threshold of this code can certainly not be better than the threshold of the code I had beforehand. Okay? And in general will be, of course, worse. But now what is the threshold of this code, right? So remember, this is now a code that has, this is degree 2 and this is degree 4, right? So this is what's called a cycle code. It's a code that has degrees 2 in the variable node, and someone had asked beforehand about it. And it's a 2-4 regular uncoupled code. And for the binary erasure channel, we know explicitly you can compute fairly easily what the erasure probability is. And for the threshold, and it's 1/3. Okay, so this code can decode up to 1/3 erasure probability. Not something record-breaking because the whole thing is supposed to rate a half code, so it's not a very good performance. But for sure, up to rate a third, we can do it. So, but now what does this mean, right? So now let's look. So assume we do an erasure probability less than a third. So then with high probability, we can decode this part here. Okay. So, but now looks what happens, right? So if we have decoded it, and we have decoded the first section. But once I decoded the first section, I can simply take all the messages to go to the right and simply put them into the checks. That will just, say what this thing were. But what I'm left with is exactly a code that looks exactly the same as beforehand, right? So if I decode like this, then I know that the threshold of this code must be at least a third, right? Okay, not, as I said, nothing, to write home about. But what is interesting is what happens now if the degrees become larger, right? So let's assume I have a 612 here. And now I draw here an 816 code. Okay, so again, it's already half, but the degrees become larger, right? The point is that I can play exactly the same game with this, right? I can simply erase all this part here. And what I've left with is, again, exactly this part here. It's exactly the same thing, again, a 2-4 code, right? So this one must also have a threshold of at least a third, right? Clear? All I do is I'm simply erasing all this part here. What I've left with is just this variable node, this check node, this variable node. It's exactly what I had before. And this has an erasure probability of at least a third. Now, once I've decoded it, the rest is exactly just what I had before, but with one section taken off. Okay? So also this has an erasure probability of a third. And this is true no matter what I'm picking here. I can pick 100, 200 code here, right? Then again, this must have a threshold of at least a third. So the uncoupled case, okay, if I pick those, whatever, the 8, 16, whatever, right? I can find, for large enough degrees, the threshold is certainly less than a third. It goes actually to 0, right? But for this one, if I'm looking at the coupled version, no matter what the degrees are, okay, this will be at least always a third. Okay? Now, if it was just a third, this would not be super interesting because it's very easy to come up with a code that's threshold a third if it's already a half code. Okay? But it indicates that there's something interesting happening, right? That this coupling actually had some effect, right? Because otherwise, if it wasn't for the boundary condition, as I told you, it would behave in exactly the same way as before. Okay. What's actually the time?
3:20.
Huh?
3:20.
And I'm basically done.
10 minutes.
Okay. So I have 10 minutes or something? Okay. Okay. Can you just tell me? Okay. Good. So, so now what you can do is you can do exactly the same for what I told you before. And so we can do dense evolution, this recursion for this case than what I had beforehand. Okay. We can do exactly the same game as beforehand. And so now the only thing that becomes a little bit more difficult is because now I don't have just a single x. Since I have a boundary here, these erasure probabilities will not be the same. They will depend on where in the structure, in the local structure it is, okay? Something in the middle will not be the same as something at the boundary. And so now when I write down dense evolution, I cannot just write a one-dimensional recursion, but unfortunately it's a vector recursion, right? So I have for every position, I have one x now, and then for every position I have one y, and now I have to write down these recursions, okay? But other than that, it's exactly the same. So now these recursions will be, because these messages coming in, will now come, they will have now different roles. And so now what I have to do is I have to actually average over all the various neighbors that it could come from. Okay, but otherwise it's exactly the same. I have to just replace the y with the average over the y's, and the same thing here, right? And so if I write down now, the recursion looks exactly the same, but they have 2 times these averages in here, right? So I have now a vector recursion rather than a scalar recursion. Okay, so let me show you now how this actually behaves. Okay, so we just know that it behaves better, but now what is actually how is actually the behavior? So this is the experiment. I have this code here as a particular length. I think in this case it's maybe 100 or something, fairly long. And it's again the erasure channel, again 3, 6, everything is the same, and here I'm plotting the exit function. But now the only difference is that before I had a single value. I had just one of these things. I had a single value because a binary, it was a scalar recursion. Now I have a position, right? For every position of these 100 codes, I have a different x, right? So this x are the x's from the boundary, this is the x's in the middle of the code, and this is the x's on the other boundary, okay? And so what I will do now is I will now start decoding, and these x's will go down, they will still be monotone, but they will not just be flat, okay? They will take a shape depending on how this thing behaves. So let me just run it. And I run it below the threshold of the uncoupled code, okay? So let's run it. So we'll see it goes down, and essentially, except for a little thing at the boundary, let me play it one more time, it basically goes down like a constant, okay? And the way it goes down is exactly like the uncoupled code, okay? So these numbers that you see is exactly what you would have seen in the recursion of the uncoupled code, okay? You see a little bit something at the boundary because at the boundary things are a little bit different, okay? But that's it. So far, not so super interesting. But now let's see what happens if I'm actually decoding above the threshold of this uncoupled case. Okay, so now let's play this movie again. So now what we see, it does it, and it actually in the middle gets stuck. And this thing it gets stuck would be exactly where it gets stuck in the uncoupled case. But now you can see that at the boundary, things actually don't get stuck. At the boundary, you can actually decode. And this is like a wave, okay? Just think of a continuous function that moves at constant speed inside, and it does the decoding. Okay, so it does it, this wave moves from both sides at constant speed inside, does the decoding, and eventually succeeds. Okay, and so this happens above the threshold. Now, how high enough does it happen? Well, this is something we'll talk about on Thursday. It turns out that it happens exactly up to the math threshold of the underlying code. So if you take a 3.6 code, and if you had done a map decoding, so the optimum decoding of the 3.6 code, the uncoupled one, then its threshold would actually be better than the coupled, if you do the iterative decoding, which is suboptimal. Okay? So instead of the 43%, we'll learn that you can do about almost 48 or almost 49%, right? If you had done the optimum decoding. And so it will turn out that you can actually do this decoding up to it. But if you, of course, go above the map threshold, then, of course, at some point you will simply be stuck. And even this magic at the boundary will not happen anymore, and you will simply get stuck. And what you get stuck in here is exactly the same point that you would have gotten stuck if you had the uncoupled code. Okay? So I guess let me just show you still this picture and finish with this part. So remember, I started with this metastability. Okay, so just let me give you one other example where this metastability happens. And I'm sure many of you have seen it already on YouTube. You can take water that's fairly clean, put it in a very clean container, and then put it in the freezer. And if you put it in the right number of hours in the freezer, the water can actually become less than 0 degrees, okay, and still not freeze, okay. And it will be again in this metastable state. It's called supercooled water. Now, eventually, the water has only maybe a few hours, depends on the parameters, that this stays in this metastable state. So eventually, it will actually freeze. But if everything is very clean, it needs something to actually freeze, like a seed or some initialization. Okay. And so when you do this and you take then the bottle out, then you can actually start, and that's what's here in one of the YouTube videos. There are many ways of doing it. You could either put a seed in there, you've seen, or you could simply bump it, so you give some extra energy to it. And then once you start this, it will start from this nucleus, from the top you will see, and will start the freezing. And that's exactly the same as the decoding wave that happens. So you bump it, it will start from the top, it will go down at constant speed, and will do the decoding. Okay, and so this process is exactly the same process that you see on the left, which is the decoding process. It's just the physical incarnation of this nucleation process that happens here. Okay, so that's basically the physics that you have in thing. If you look at it exactly, this is not exactly frozen. Why is it not exactly frozen? Because when it goes from the metastable state to the stable state, it actually gives off the heat, right? I mean, it gives off the energy, and that will reheat it again, and that's why we'll get actually a little bit more like a slush rather than actually something very crystallized form. Okay, so let me maybe skip this. Let me start here. So let me just finish the thought. So we take an uncoupled ensemble. We learned how to analyze it for the binary erasure channel. We learned that we can take this graphical model and couple it, and then do something special at the boundary. And then we learned that it behaves in a fundamentally different way. And the claim is that it behaves as if you had taken this code and did map decoding. So you're taking the underlying code, whatever the 3.6 or whatever the code is, and you had taken map decoding. And then the threshold that you get now is actually the map decoding threshold. Okay? On the downside, we have some rate loss. Okay? So we gain, we can gain substantially perhaps in threshold, but on the downside, of course, we have some rate loss, and so now we have to then, first of all, figure out why does this happen, why is it the map threshold, what can we do, what is the rate loss, etc., and what might be some of the open prompts that we have. Okay, so thanks a lot, and I hope to see many of you still first.